Okay, so today we're going to discuss our next topic, quadric surfaces. These are more general surfaces than just lines, than just planes that we discussed last time. But first thing that I want to do is to do one additional example related to lines and planes. And so this is what I want to do. Let's say we have a line, and the line maybe has an equation x minus 1 over 2 equal to y plus 2 over 1 equal to z minus 2 over 3. And also we have a plane, 2x minus y plus z equal to, let's say, 4. And what I want to do, number one, actually one more thing. And let's say we have a point P with coordinates 1, 2, 0. And I want to do a couple of things. So number one, I want to find the point of intersection between the line and the plane. That should be relatively easy to do. So first of all, if you want to find the point of intersection, that means a point has to belong to the line and to the plane simultaneously. So I should be able to take a point on the line, plug it into the equation of the plane, and make sure that the equation is satisfied. The only problem here is that I'm not really sure how to input the symmetric equation of a line into equation of a plane. So first thing that we'll do, we're going to change the symmetric equation of our line to the parametric equation. So we set all the fractions in the symmetric equation equal to t, and then solve for x, y, and z. So if you do that, then x will end up being 1 plus 2t, y will end up being minus 2 plus t, and solving the equation for z, the last equation here, z is 2 plus 3t. So given t, this is the equation of the particle that moves along my line. And so now I want to determine when this particle is also on the plane. So that means that I need to take all of this and plug them into the equation of the plane, which is 2x minus y plus z equal to 4. So that is 2 times 1 plus 2t minus 2 plus t plus z 2 plus 3t equal to 4. And so now I need to solve for t, so distributing 2 plus 4t plus 2 minus t plus 2 plus 3t equal to 4. So how many t's have I got? 4t plus 3t minus t, that is 6t. Then 2 plus 2, 4, plus 2, 6. Take 6, move to the right, and you get minus 2. And so the particle crosses a plane when t is minus 2/6 or minus 1/3. And so therefore the point that I'm looking for, the point of intersection, I'm going to get by taking this value of t and stuffing it into the equation of a line, into the parametric equation of a line. And so we're going to get that x is 1 minus 2/3, y is minus 2 plus or minus 1/3, and z is 2 plus 3 times minus 1/3 minus 1. So x is 1/3, y is minus 7/3, and z is 1. So the answer is a point 1/3 minus 7/3 and 1. And then the second part of this question, let's say I want to find the distance between my point P and the plane in my example, which is once again this. And there are a variety of ways of doing it, and one of them is the following. So let's say this is my plane, and this is my point P. If I want to find the distance from P to the plane, I need to drop a perpendicular onto the plane, and then measure the length of that perpendicular. So this length is my distance. Well, another way to think about it, I can find the equation of a line L, which passes through P and is perpendicular to the plane. Find the intersection between this line and the plane, and then measure the length, the distance from P to the point of the intersection. So let's try to do that. So let's say the point of the intersection I'm going to call R, and the line that is perpendicular to the plane is going to be L. So part A, find the equation for L. And that is very easy to do because to find the equation for L, I need to know a point that is contained in L, and that's a point P, which is given to me. And then I need to find a vector in the direction of the line, but because the line is perpendicular to the plane, from the equation of a plane, I can pick a vector perpendicular to the plane, and that is 2 minus 1, 1. So that's V in the direction of L. And my point P, again, is this one. So P like that is an L. So we have two facts, this one and that one, and so therefore the equation for L, and I'm going to write again parametric equation in a view of what we have done in the previous part. So P is an L, V is an L, so the equation for L is going to be x equal to x component of P, 1 plus first component of V times T, y is the second component of L, minus 1 times T minus T, and then Z is a third component of L, 0 plus 1 times T, so that's just T. So that's the equation for L. Then the second step, I want to find where L intersects my plane. So the plane again is 2x minus y plus z equal to 4. And just like in the previous sub-example, I simply need to take the equation for L and plug it into the equation for my plane. So 2 times 1 plus 2t minus 2 minus t plus t, that is equal to 4. If I distribute, this is 4t plus 2 minus 2 plus t plus another t equal to 4. 2's cancel out, and we have 6t equal to 4. So t is 4/6, or 2/3. Take this t, insert it back into the equation of the line, and that gives me the point of the intersection. So x is 1 plus 4/3, right? 2 times 2/3. Y is 2 minus 2/3, and z is 2/3. And so the point of the intersection, which I think I called R, so R will have coordinates 7/3, then 2 minus 2/3, 4/3, and 2/3. And so the last step in this program is that I want to find the distance between P and R, right? And that would be the distance from the plane to my point. So number 3, find the distance between P and R, and so length PR is going to be just a distance formula, so it's a square root of P was 1, 2, 0, so 1 minus 7/3 square plus 2 minus 4/3 square plus 2/3 minus 0, so just 2/3. quantity square, whatever this is. I'm not going to simplify it. So that's a way to find the distance from a point to the plane, find the equation for a line that is passing through the point perpendicular to the plane, find where this line intersects the plane, and then compute the distance between the point and the point of the intersection. We will see relatively soon that actually there is another way to find it at the same distance, which is going to be much less involved than this. Okay, so moving on to quadric surfaces. So as you have already noticed, I suppose, equations of lines and planes are linear. So in particular, an equation of a plane, x, y, and z, appear as the first part of these coordinates. Quadric surfaces will be surfaces that are defined by equations that are at most quadratic in x, y, and z. So any surface with an equation ax squared plus b y squared plus c z squared plus dx y plus e x z plus f y z plus, so this lists all possible second powers of x, y, and z, so all possible products of first powers of x of different coordinates and all of their squares. Plus you can also have the first order terms, gx plus hy plus I z, and then you can have a term without the coordinates, so plus j, and the whole thing is equal to 0. So any surface of this kind is going to be a quadric surface. It has to be true that A, B, C, D, E, F, one of these would be not 0, because if all of the quadratic terms are going to be 0, then what is left is the equation of a plane, right? Gx plus hy plus iz plus j equal to 0. Okay, so I'm going to do a bunch of examples. In principle, if you want to classify the resulting surfaces, then the classification will depend on the values of A, B, C, D, E, and F, who is negative, who is positive, who is equal to each other, who is not equal to each other. So if you look in the book, in the section for quadric surfaces, there is a table which, for every choice of these coefficients, which describes how the surface will look like and classifies it. Instead of doing the full classification here, what I'm going to try to do today is simply to sketch a few examples and give them names, and just give you an idea of how to sketch these quadric surfaces, even if you don't know how to classify them. So we're just going to do a bunch of different examples. But before I do these examples, let me just remind you a couple of things. So first, actually, still an example. What if I have an equation x squared plus y squared plus z squared minus r squared equal to 0. So that's a single equation in 3D, as we previously discussed. That means that this equation will define one surface. And is this surface recognizable? And I claim yes, because we already sketched this surface before. If I take r squared and I move it to the right, I'm going to get x squared plus y squared plus z squared equal to r squared, and that is a sphere centered at the origin with the radius r. So that's your first example of a quadric surface. Okay, let me see what's going on here. Sorry. Just need to figure out something. Okay. All right. So let's now try to plot some other examples. Well, actually, before, as I said, let's recall one issue. So recall. If I have an equation, let's say z equal to, or not z, equation x squared plus y squared equal to 1. And I think about this equation as being defined in 3D, then in order to sketch, and okay, so this is again a single equation, so it describes a surface in 3D. And the special thing about this equation is that z is missing from here. And we discussed that in this case, what you need to do is the following. So if I want to sketch the corresponding surface, I notice that my equation here, as I said, does not involve z. So what is x squared plus y squared equal to 1? In xy plane, that is an equation of the circle, right? Circle of radius 1. So I'm going to draw it. So this is 1 and that is 1. But because z is missing, if I make z equal to, let's say, 2, if z is equal to 2, then that gives me a plane. Let's use a different color here. It gives me a plane at the level 2. But for that plane, still, so z is 2, but x squared plus y squared is still equal to 1. So in 3D, I would still see the same circle as I saw before, except that this circle is now going to be in the plane. Sorry, this doesn't seem to work. Let's try again. Okay. The circle is in the plane z equal to 2. And so it doesn't matter at what level I draw a plane z equal to something. Within that plane, I still need to draw a circle x squared plus y squared equal to 1. And so that means that my surface is actually a collection of infinitely many circles like that. If I connect all of them, what I'm going to get is a cylindrical surface like this. So if you want to sketch an equation, if you want to sketch a surface corresponding to an equation in which z coordinate is missing, what you need to do is to simply draw a graph of this equation in xy plane, and then move this graph up and down, and it will will sweep the surface. So in this case, that surface is a cylinder. So and this is going to be our second example of a quadric surface, right? Because x squared plus y squared equal to 1 means that I have at least two coefficients in front of x squared and y squared that are not equal to 0. So it is a quadric surface, and it ends up being a cylinder. So the next example, again, let's assume that one variable is missing. So maybe z is equal to y squared. Again, that's a quadric surface because at least there is at least one square of the coordinate. And let's say I want to sketch that surface. So here immediately I notice that x is missing. And if x is missing, that means that in any plane x equal to something, any plane perpendicular to x-axis, I'll still see exactly the same relationship between z and y. And so to get this surface, I'll simply need to sketch the surface z equal to y squared in zy plane, and then move it along x-axis, meaning forward and backward, and then this will generate my surface. So this should be fairly straightforward again, because z equal to y squared, that's a graph in zy plane, and that's a parabola, right? So it's a parabola like this. And or like that. And so now I have to take this parabola and shift it up and down x-axis. And let's do that. So you shift it here, and you also shift it in the opposite direction there, and then you just connect these parabolas, right? And this is going to generate for you a surface which is parabolic in shape. So moral of the story here is whenever one of the variables is missing, you generate the graph of a surface by plotting the graph in the plane of the remaining variables, and then moving it along the axis corresponding to the variable that is missing, and therefore you always end up with the surface that we're going to call a parabolic surface. So this is a parabolic surface. So no matter what the graph is from which the variable is missing, the outcome is some sort of a parabolic surface. Okay, next example. Let's now have a full equation like this. X squared plus y squared, but now I'm going to add the z squared, but with 1/2 in front. So plus 1/2 z squared equal to 1. And my question is, what sort of surface would this be? If you didn't have 1/2 in front of z squared, then it would be easy because it would be just a sphere. But now you're multiplying z squared by 1/2, so that means that you somehow rescale the z-axis in the sphere, and that means that you're stretching or compressing the sphere along the z-axis, and instead of a sphere, you get sort of a squished or stretched sphere, whatever the case might be. And we need to try to reconstruct this shape as well as we can. Well, so the tool in this case, no variables are missing. The tool is to try to identify cross-sections of this surface by planes that are perpendicular to different axes. So, for example, consider cross sections of this surface let's say by planes parallel or perpendicular to z axis. Planes perpendicular to z axis are parallel to xy plane. So a plane parallel to xy plane will have z constant on that plane. So z is equal to some k. So I want to identify a graph that I'm going to get by taking this quadric surface and intersecting it by plane. So intersection of two surfaces clearly is generically is a curve. So I want to find the curve which lies on the intersection of this surface and that surface. And so coordinates of points on that curve will have to satisfy both equations. So I want to find all points x, y, z, satisfying both equations at the same time, and therefore satisfying this system of equations, x squared plus y squared plus 1/2 z squared equal to 1 and z equal to k. Well, then I can always stuff z equal to k into the first equation, so I'm actually looking at all curves in 3D that satisfy the equation x squared plus, actually not in 3D, in 2D, right? Because now it is in x and y coordinates. Satisfying x squared plus y squared equals to 1 minus 1/2 k squared. Well, and in this case, you see that x squared plus y squared on the left is a quantity that is always positive. And Sorry. And therefore, the quantity on the right must also be, well, x squared plus y squared is non-negative, so 1 minus 1/2 k squared also has to be non-negative, so it should be greater or equal than 0. And so that means that 1/2 k squared has to be less or equal than 1, or k. So k squared is less or equal than 2. So k, if you solve this inequality, is between minus square root of 2 and square root of 2, right? So if k is like that, then we guarantee that 1/2 k squared is less or equal than 1. And so 1 minus 1/2 k squared is greater or equal than 0. Okay, so but then for any k like this, between minus square root of 2 and square root of 2, the equation looks like, again, x squared plus y squared equal to 1 minus 1/2 k squared, and that is an equation of a circle in xy plane. The circle is centered at the origin, and it has the radius square root of 1 minus 1/2 k squared. Okay, so let's see if we can sketch the resulting surface just by having this information. Let's do it on the next page. So I'm intersecting my surface by different planes at a level z equal to k, and I discovered that this equation is only legitimate as long as k is between minus square root of 2 and square root of 2. So that means that any plane with z less than minus square root of 2 or bigger than square root of 2 is not going to intersect my surface. And so what I'm going to do then is to label z equal to square root of 2 and z equal to minus square root of 2 on z-axis as points beyond which, if I go up or down beyond these points, I will not see any of my surface. Okay, so then let's think what we're going to get if k is equal to 0. So if k is equal to 0, for example, then the circle that I'm going to get is going to be x squared plus y squared equal to 1. And that's a circle of radius 1. K is equal to 0, so I'm in xy plane. And so I'm going to get something like this. And this is 1, and that is 1. When k is equal to, let's say, 1, I'll have x squared plus y squared equal to square root of 1 minus 1/2. So that is 1 over, so the radius is, sorry. The circle has an equation 1 minus 1/2 k squared. So this is x squared plus y squared equal to 1/2. So radius here is equal to 1. And the radius here is 1 over square root of 2, right? So it's a radius, some radius less than 1. We'll sketch a circle, so this is still a circle. And the third circle that I want to highlight is k equal to square root of 2, because if k is equal to square root of 2, then you plug that into the equation for the radius and you'll get 0. So radius equals 0. Okay, and so now you hopefully see what the shape is going to be. If I am at a level z equal to 1, right, or k equal to 1, so I'm somewhere here, I see a circle with a radius 1 over square root of 2. That radius is smaller than 1, so it's probably something like this. And in fact, as I keep increasing k, then the radius is going down, right? And it becomes 0 when k is equal to square root of 2. So even smaller radius here, and then eventually it is 0. So if I connect all of these circles, I'll get something like this, and then something like that. And then, of course, I'll get exactly the same thing on the opposite side of a z-axis, because my equation originally has z squared in it, so if I plug in plus or minus z, I'm going to get exactly the same expression. And so I just continue the surface downward. And so what you see is that this essentially is a sphere, kind of like a sphere, but in this case it's stretched along the z-axis. So the distance that the sphere, that the surface covers along the z-axis is from minus square root of 2 to square root of 2, but along x and y-axis it is from minus 1 to 1. So it is kind of a stretched sphere along the z-axis. This is called an ellipsoid. Where does the word ellipse comes from? So now let's do one more thing. Consider a cross-section of this. By the plane, let's say, maybe x equal to 0. So if x is equal to 0, that this defines y, z plane. And so what sort of shape will I see if I do this cross-section? That means that I have to take x equal to 0 and use that in my original equation. So if x is equal to 0, then I get y squared plus 1/2 z squared equal to 1. And if you recall your geometry, this is an equation of an ellipse. In YZ plane. So if I do a cross section of the surface in the YZ plane, it's going to be now this ellipse. Same thing for XZ plane, right? For XZ plane, I'll get x squared plus 1/2 z squared equal to 1. That also is an ellipse. So overall, if I take this ellipsoidal surface, I take cross sections by plane parallel to XY plane, I'll see circles. I'll take cross sections by plane parallel to XZ or YZ plane, and I'll see ellipses. Okay. Another example. Let's do the following. Actually, before I do another example, let's see if we can actually sketch that surface that I just described. So it was x squared plus y squared plus 1/2 z squared equal to 1. And ta-da, you see exactly the surface that I just described, right? This is an ellipsoid. It's stretched along z-axis. And if I look at it from the top, then I see circles corresponding to cross sections of this surface by horizontal planes. If I look at this guy the cross section of this guy by vertical planes, you see ellipses, right? Ellipses elongated along the z-axis. So our methodology seems to produce the right picture. Okay, let's move on to another example. Let's say now I have the following equation: x squared plus y squared minus z squared equal to 0. Would the similar approach work for this? Okay, and the similar approach means that I'm going to try to take this surface, right, defined by this equation, and then consider cross sections of this surface by various planes, horizontal or vertical. So, cross sections by horizontal planes will require me to set z equal to k, and if I plug that into my equation, I'm going to get x squared plus y squared. If I move z squared on the other side, x squared plus y squared is equal to z squared on the plane z equal to k. Z is equal to k, so I get k squared. And of course, that is a circle of radius k, centered at the origin. Of xy plane. Okay, so that means that if I take my surface and I intersect it by any horizontal plane, I will get a circle. Not only that, but as k gets bigger, the radius of a circle gets bigger, right? In fact, the radius of a circle is always equal to k, right? So intersection of a plane, of a surface by a plane z equal to k produces a circle of the same radius, k. All right, so that gives me cross-section by by horizontal planes. So now let's look at cross sections by some vertical planes. In particular, I'm going to look at the planes x equal to k, right? So these are the planes perpendicular to x-axis at the level k, and likewise I can do surfaces perpendicular to y-axis, y equal to k, but in this case you're going to get exactly the same thing, so I'm just going to do it for x equal to k, and then we're going to extrapolate to y equal to k. So if I set x equal to k, then my equation becomes k squared plus y squared minus z squared equal to 0. And that is the same thing as saying z squared is equal to y squared plus k squared. And then solving for z, this will give me z equal to plus or minus square root of y squared plus k squared. Okay, what is the shape of that graph? So one thing that is sort of clear is that the graph is going to have two branches. One is with positive z, and another one is with negative z. I'm going to look separately at different cases. If k is 0, then z is equal to plus or minus square root of y squared. And square root of y squared is actually absolute value of y, so z is equal to plus or minus square root of y. On the other hand, if k is not equal to 0, so for example, k is equal 1, then my z is square root plus or minus square root of 1 plus k squared. What sort of a shape is that? So in principle, no, that's not true. 1 plus y squared. So k is equal to 1, so 1 plus y squared. In principle, you can just use a graphing procedure if you don't recognize this. Or we can simply try to, roughly speaking, sketch this shape on YZ plane. So z being equal to square root of 1 plus y squared is a positive number. So the expression inside square root is always greater or equal than 1. So if I take z with a plus sign, then that means that I'm going to get a graph which always exceeds 1, right? Which always lies above z equal to 1. That's number one. And number two, as y gets very big in 1 plus y squared, if y is very big, 1 really doesn't matter, right? So for large y, z essentially looks like square root of y squared, which is either y or minus y, or just absolute value of y. So that means that if z is large, if y is large, then z is very close to y or minus y. And again, if I keep the sign of z positive. And so if you think about this, this means that the graph, will approach the axis z equal to y, or z equal to minus y if it goes to plus or minus infinity. Same behavior, of course, you get below the y-axis because I have z plus or minus the same thing, so the graph is symmetric with respect to the y-axis, so you get something similar downstairs. And if you remember the terminology, then these two graphs are called hyperbolas. Okay, so now we should be able to sketch the surface. So, well, actually one more thing, right? So as k gets bigger, I'm still going to get these hyperboloids, except that instead of 1, I'll have k squared, k bigger. That means that the graph lies above z equal to k. So as k gets bigger, these hyperbolas are going to shift up, and these hyperbolas are going to shift down. All right, so sketching the final answer. So if I take cross-section by zy plane, we said that we're going to get by zy plane itself, we're going to get this graph. Z equal to plus, I don't know why I wrote square root of y, plus minus absolute value of y. So we're going to get z equal to plus or minus absolute value of y. So I need to sketch that in zy plane because that is going to be my intersection with zy plane. That's plus absolute value of y, and this is minus absolute value of y. And then I'm going to do the following. I am going to just use now the cross sections by horizontal planes, which we said are circles. So at a level k, you get a circle of radius k. So if I'm, for example, at a level 1, my cross section by horizontal plane is a circle of radius 1 like this. If I'm at a level 2, cross section is a circle of radius 2 like that. If I'm doing the same thing below xy plane at the level minus 1, I still get a circle of radius 1. At the level minus 2, I get a circle of radius minus 2. Okay, and what shape is that? So as I keep going up, circles grow in radius. If I go down below xy plane, circles are going to be increasing in radius. This is a cone. And now, if you think about it, if you take a cross section of the cone by plane x equal to k, right, a plane parallel to xy plane, you indeed will see hyperbolas like this. But they're difficult to draw on this picture, so I'm not going to do that. So you just use the minimum amount of information possible from these different cross sections to surmise what the shape of your quadric surface is going to be. And last, let's just see if we can plot the same thing here. So the surface was x squared plus y squared minus z squared equals 0. Well, that's exactly what we just got, right? It's a cone. And if I look at cross sections of this cone from above, I see circles. If I look at cross sections of this cone from the front, guess what I see? I see these hyperbolas. I see absolute value of x, right, as two lines bounding my cone from the sides, and then otherwise I see hyperbolas. So everything seems to match. Okay, and so this is a procedure that you can use in general to draw any quadric surface. And as I said, take a look in the book at the table of how the quadric surfaces are supposed to look like based on the choice of the coefficients. Thanks.